passa para esse lado, olha aqui, ele pega o topo do quadro, não, porque 2 vezes falaram. Okay, hello everybody. So today we continue the topic of finite time blow-up, finite time blow-up in incompressible Friede Euler equations. So essentially, I would like to continue the idea of studying this question about. So first of all, let's just repeat the equation. So we have considered 3 dimensions, and the Euler equations is, you remember, so this is this compact set of equations. So the Euler itself and the incompressibility condition, which we consider the blow-up, the question of blow-up far from boundaries. So there are no boundaries here. So it's either the full space or the 3-dimensional torus, or the periodic boundary conditions. So what was the idea? So the idea was that, okay, so we don't understand what happens, and the problem about this equation is that not only we don't understand what happens, but we don't even understand what most likely to happen. So that's actually the bigger trouble. So the question, if there is blow up or not, and if there is, so what it looks like. So there is, as I said, there is good progress in analytical studies. So there is, we know that there are initial conditions which lead to blow up, point time blow up. If the initial conditions are differentiable, but not much more than that. So if there is a certain singularity beyond the first derivative. At the same time, it still doesn't answer the question, because you don't know how generic is this blow up, how typical it is. So it would be nice to know if there is or not, if there is blow up from typical initial condition or not, because it's essentially, since Euler is obtained for as a limiting case of 0 viscosity from Navier-Stokes, so that's a central question for turbulence. Because if there is global solution, then we just put viscosity to be 0 and work with Euler. And if there is, also there are questions here, but anyway. And if not, then we should do something different. So so we were trying to understand this issue last time with a simplified model. Or sometimes they call toy model. So a simplified model is that you try to put a different model, different equations, which in one or the other way resemble the initial system, but it's much simpler, so you can study them in some way. Because the problem with Euler that we cannot, we're limited in the analytical study. We're also limited in numerical study. So we actually do not access in any form the equations. So we find simplified model where we can access and find an answer one way or the other. So what we did the last time was studying the shell model. So the shell model was obtained by considering wave numbers. Wave numbers which were just powers of 2. And this shell, because it's kind of, you consider in your 3-dimensional space the concentrical spheres of this radius. So it's 1, 2, 4, and so on. And this substituting instead of in periodic torus, you would have the vector, three-dimensional vector of integer components, right? So it will be some grid, but instead of grid, we consider concentrical spheres, which just become bigger and bigger in geometric progression. So you can capture the same resolution, but with much fewer variables. So the equations was obtained by mimicking structure. So essentially scaling laws, structure, and conservation laws. Conservation laws of 3D Euler. So we construct by hand the equations of motion with this type of variables. We're trying to mimic the structure of 3D Euler equations. Essentially, we mimic the fact that it's quadratic. And conservation laws, if you remember that we can incorporate conservation of energy, conservation of helicity, and the result was that there is a self-similar blow-up. Blow up, which is essentially no good because this is bad. Because this is not what we see in 3D Euler. So 3D Euler, the numerical simulation that we have with accessed by very strong computers, they do not look self-similar. Okay. It looks more like burgers, and we will see that it's actually there is quite good reason to this. So we are partially succeeded. So we succeeded to see blow up, but it's not the blow up we want. So today I will explain another work. This is recent. Another strategy to make a model and see what is the blow up. So this is. So if you want to see I will give an idea. So if you want to see the details, you can take the two papers. So this is physical review letters, 2018, and nonlinearity, 2021. So these are both of Campolino and myself. So the Ciro Campolino is our student. So I will explain you what we did, and it is a quite different strategy. So so what we want to do is let's assume that this shell model gives blow up, but it's not the blow up of 3D Euler because it's not good enough. So it's not close enough to the original Euler. So how to make better model? So the question is, how can we design a better model? A better toy model for 3D Euler. So This is the question. So the strongest point that was relaxed here, essentially, is that we gave up with the structure of the equation. So this structure that is incompressible field, that there is a pressure, that there is a form of the convective term, it was completely forgotten. All we left is that we just use that it's quadratic, that's it, and that there are some conservation laws. So now, on the next step, we actually want to recover this. So I want to keep exactly the same equation. So the idea is to use exactly the same system, the incompressible exactly equations of 3D Euler system. But if we use equation for 3D Euler system, but it's not 3D Euler, what we can change actually is the space. So we use this system for 3D Euler, but in a different space. But in a different space. So we need to simplify the space. So we simplify the space, not equations. Okay. So essentially, what we will do, instead of three-dimensional space or three-dimensional torus, we consider something different, which will be three-dimensional, but neither one. So we will construct something simpler, and in this step we will follow the idea of the shell model. So that what we do is instead of the what we do. So we will, instead of Fourier coefficients which were integer. Remember, the Fourier coefficients, they were integer numbers. So this, let's say, 0, 1, 2, 3, 4, and minus 1, 2, and so on. So instead of these coefficients, we will take the coefficients but which fill the same line, but in much more rare situation. So our model will be, so we put 1 minus 1, that we keep 2, but then we take 4, and then we take 8. So it's 1, 2, 4, 8, and minus 1, minus 2, minus 4, minus 8. So we define our space will be lambda, which will be plus minus power lambda n, where n is integer number positive. So essentially, this will be plus minus 1, plus minus lambda, plus minus lambda square, and so on. Well, lambda is some number positive, not bigger than 1. So not necessarily 2. So it can be free of whatever. So what we will do is, instead of the wave numbers which are integer, we will use geometric progression. So the difference is rather clearly seen from this picture. No? So if you want, for example, to study the domain up to 1,000, in the original formulation, you need 1,000 variables. And here we will only need 10. Right? So we decrease the number of variables logarithmically. Okay, so what you do? So now we can understand what means, what are the functions in this space, functions. So in order to understand what are the functions on this space, we start with functions that we're used to. So consider a function. So we start with a function which was in our torus. So it's a periodic interval. Let's say two real numbers. The function f of x. Right. So how we proceed in order to get to our space? So first, we make Fourier transform. So we take Fourier coefficients. Fourier transform, or coefficients in this case. So Fourier coefficient, you know what it is. So Fourier coefficient is what? Is fk is 1 over 2 pi, integral from 0 to 2 pi, f of x, exponent minus e kx dx. And this is for k integer. So any integer number. So that means that Fourier coefficients give another representation of this function, which will be, so we put hat of k, and in other words, f is a function from integer numbers, which gives you index of the Fourier coefficient, to complex numbers. So it's complex. So this is another representation of the same function. So whenever you have a function on a circle, it can also be represented as a sequence, as a sequence of Fourier coefficients. So now what we consider is, we want to substitute the line of coefficients by the line of geometric progression of numbers. So we consider functions f of k, where f, so where k will be from here. So in other words, f, in our case, f will be function from this space to complex numbers. So this is a substitution of the usual functional space by the new functional space. And now we want to add a structure to this space in such a way that we can make sense to the Euler equations. So we change the space, but we have to put some structure to the space so that the space will be good enough in order to study the fluid dynamics in this space. Good. So, yeah. No, força como se fosse chapéu. Yeah, but in our case, okay, I can keep chapéu. Okay, if you like. Mm-hmm. But I want to forget about head because it's our functions. Okay, but our functions, they somehow will mimic the Fourier transforms rather than the physical space. Okay, so what do we have for the functional space? So new functional space. So what do we have? So first of all, it's a linear space. It's linear. Because we can, since functions are determined in the same way, so you can define a sum of two functions, right? Which is just sum of the values. So there is no problem of defining the sum. And multiplication by a number. So the gamma f of k is also, for any complex number, you can just multiply the function. So we have a linear structure. Then we have a scalar product. Scalar product, so for the scalar product, remember that f and g, which we write just exactly in a way how we do it in a Fourier space. So it will be sum of f of k j minus k and sum in a Fourier space, we would sum over all integers. Now we sum over all lambda. And automatically, you can find that this scalar product satisfies the linear relations. The next, we can define derivatives. So derivative, let's remember what is derivative in the remember the derivative in the Fourier transform at k is I k f of k. Remember, so derivative is just multiplication by I k. So this we also can have, and we can just do the same. So we write simply like this. Right? So if you remember, so we always have heads, but I'll be start forgetting the heads. So there are always heads. So let's start forgetting the heads, because this is our space. We have derivatives, and then what we can have is the product. We also need to, so you said, so let's see what we have here. So derivatives we have, we can sum, and we need a product. We need to be able to multiply two functions. So this is missing. So the next is the product. So the product, again, let's remember what it is. So in on a real line, you have so if you take a product of two functions, and then you take okay, so the product of if you take product of two functions, and you Fourier transform, so then you get Fourier component. So this is just what is called convolution. A convolution is exactly the sum over p plus q. Oh no, p plus q equal k. F k. Oh no, f p. Yeah? So this is a convolution by definition. It's convolution. So convolution, we can make this stuff. So in our case, for our functions, it's a question whether we can do just the same for our functions. So whether we can define the two functions in our space. So this is the question. Whether we can define it as a sum. So the problem that you immediately see, the problem is that not for any p and q from lambda, the sum not for any p of q in lambda, the sum is lambda. So for example, if you take 1 plus 2, you get 3. It's not on the space. The 2 plus 2 is 4, okay. But 1 plus 2 is not in the space, and 1 plus 4 is also not in the space. So you cannot just directly give this sum. So we will actually try to solve this problem in general. So the question whether we can construct, when we can construct products in principle so that everything works. And what properties it will have. So what properties we want? So the properties of the product. So which properties you would like to have? So the first property that you want to have is that whenever you have any product, so what's the question? The question is that let us define the bilinear operation which having two functions give you a third function. Bilinear operation which defines a new function, and we want to construct this product satisfying certain properties which will allow us to use all the equations. So the first is that the convolution at minus k should be complex conjugate to convolution at plus k. And remember, this is what's called, this is what I forgot to say. So a new functional space. So in our functional space, if f and j satisfy this condition. So this is what's called a reality condition. So remember reality conditions from Fourier transform. So if you Fourier transform real functions, it should be complex conjugated at any values k minus k. So the Fourier coefficients of n minus n, they should be complex conjugated. So we want the product to preserve this property, because the product of two real functions would be a real function. So this one. Second property is that it should be bilinear, which is somewhat very basic. So whenever you take a linear combination of the two and take a product with the third, so it should be bilinear. So it should be fh plus gamma gh. So bilinearity. The third property you want to have is that product is commutative. So this is doesn't matter in which is first, which is the second. So this is commutativity. Okay. Fourth property. Fourth property is already something more complicated. Let's put fourth property a bit simpler. So fourth property will be that derivative of a product should be derivative of the first by j plus first derivative of the second by j. Or derivative, okay. So it's Leibniz rule. So we need Leibniz rule of differentiation because we take derivatives in other equations, so including of the products. Okay, and the fifth condition is something interesting because it's slightly non-standard. So we want to have this stuff, f jh should be equal to f jh. So this is what is called associativity in average. And why is it so? If you want to see why is it so, we should go back to the usual functional space and see what it will mean, what it means for usual functions. So for usual functions, observation. So for usual functions f and which will be and j. So it's from interval to real space, to real numbers. So what you have, remember that the usual way to put a scalar product is an integral. Right? And if you want to see associativity, so usual associativity for the three functions, it means that the product of a, f, and j, h, you can do it either like this, or it doesn't matter in which order you multiply. Okay, so in our space, it would be f j h equal f j h. So there is a problem that we can prove that it is not possible. So we can prove that we cannot create a product in our space lambda which satisfies associativity. So this is the trouble. So you cannot make it associative, and normally you never recognize, but associativity is used a lot in our derivations of fluid mechanics. So if you cannot just simply give away this property. So, but actually, what is used mostly in fluid mechanics is not associativity, but a slightly weaker property. So let us just, instead of asking for this, let us ask that this equation is equality is only satisfied in average. So it means after integration. So associativity in average. So but what it is, so this is a product, and this is scalar product. So this you can write just FGH. And here it's the same, but now it's F by GH. So this is exactly what we want to ask for. So see, so we want to preserve associativity. Associativity in normal form, we cannot do it, because we can even prove that it's not possible. But you can keep the weaker form of associativity just by keeping this equality satisfied for integrals. Okay, so this is what we do. Okay. Of course, so another observation is, of course, this all extends to higher dimension. So instead of lambda, you can take d-dimensional space. And of course, here you can define the partial derivative of any function, which is S multiplying by respective Fourier coefficient. So instead of, so in general, if you have several variables, x1, x2, x3, like three-dimensional, you just multiply by different components where this kj is just component of the vector of the dimension. So in multiple dimensions, everything works. So the interesting first result is that I will not give a proof, so I'm telling that I'm sketching the results. So the first result is a theorem. Theorem, it tells that for lambda bigger than or equal to 1.05. So remember that lambda should be bigger than 1 because it's a geometric progression. So we could not define it for any lambda, but bigger than 0.1. essentially, the belief is that it's for any, but just the proof doesn't go. So non-trivial product with properties, with these 5 properties, exist only for three situations: for lambda equal 2, lambda equal 1 plus square root of 5 over 2, which is golden mean. It solves the equation lambda square equal lambda plus 1. And the third possibility is such a number which is longer. Cubic root of 9 plus square root of 69 plus cubic root of 9 minus square root of 69 divided by cubic root of 18. So it's something like close to 1.3, something like 1.3. And it's called plastic number. So only 3 lambdas can work to create our space. And plastic number is kind of funny number. It was invented by, so it satisfies equation lambda cube equal lambda plus 1. So it was invented by a monk in Holland, something like beginning of 20th century. And it has a geometrical meaning. So if you want to split a square on similar rectangulars, you have 3 different ways. So 2 ways are kind of straight. And the third way is given by the plastic number. So this gives you a plastic number. The ratio between them. Plastic number does not mean plastic in its usual sense, because at that time it didn't exist. No, plastic means it's for some transformation. So it's interesting that the only 3 numbers that can give us the answer. And then it turns out that we can just classify all the products. So it's actually, there are not so many products. Not so many products. So in order to classify products, we need 2 more conditions. So one more condition, which are now will be conditions on a symmetry. So extra properties. So extra properties, it's the first is scale invariance. So scale invariance has to do with the transformation that we call delta lambda f, which is, so what you can do is you can define another function where you multiply lambda by the argument by lambda. And you see that since k is the power of lambda, multiplying by lambda, it still remains power of lambda. So this is a transformation stays on lattice. Okay, so the scale invariance of the products tell you that if you if you take this scaling of the product, it will be the same as product of the scaled functions. So this is also the property of usual functions. And another S2, so this is in the case of higher dimension. So what we can do? So we can make rotations. We can make rotations. So remember what means rotation. So rotation of the function. How you rotate the space? You rotate space by multiplying the coordinates by orthogonal matrix. Right? So it gives you new function just by combining them together. So the function, from function you can rotate the space and create a new function. So we want to keep this property of the overall lattice. So this is a bit more tricky property. So what I will just want to will state what it is. So we want that if you rotate the space for the product, it's the same, will be the same as product of the rotated functions. So this is f j rotated is the same as the product of f and j rotated. Like this. So it means that we have a rotation invariance. Rotation invariance is called isotropy of product. But unfortunately, we cannot just take any orthogonal matrix because we cannot just rotate our space. So remember what means our space. For example, lambda 2. Let's draw it here. For example, lambda 2 that we consider is what? It's a lattice which is geometric in both directions, and also here. So the vertices is our points of the lattice. So we cannot just rotate it because it will not stay in the same place. But we can use all matrices which are of what's so-called group of cube symmetries. So this is a group of cube symmetries. Well, in short, we want to impose some extra conditions on the product, which are also conditions for the usual matrices. So the second theorem tells that assuming the first collection of properties and also symmetries, there exists unique product up to a constant, up to the factor, up to constant factor. For lambda equal 2 and lambda golden mean. And one parameter family of products for lambda plastic number. So I have to give an example what this product means. So example. So when you consider just one-dimensional space, so what this space means, so this is, remember this is plus minus 1, plus with lambda equal 2, plus minus 2, plus minus 4, 8, and so on. So our variables, our space is 1 minus 1, 2 minus 2, 4 minus 4, and so on. So for this space, you can define a product of two functions at any k, so any k in these numbers, and it will be unique. So it has a form of f to k times j minus k plus f minus k j to k plus f k over 2 j k over 2. So this is the only form of the product that you can construct on this space, and it will satisfy all the properties. Leibniz rule, you can differentiate, you can sum, and it's associative in average and the rest. And also you can do this for other two values, for golden mean and for plastic numbers. The difference is that, you see, here the product is very simple. It only has 3 terms. So whenever you go to golden mean, it will have already more terms, I think 6 terms. And then here it will have, I don't remember, even more terms. So it's becoming richer and richer, more complex. Okay, so now we have a space, and the next step will be, so we have a space where all operations are well defined for considering equations of fluid dynamics. And then the next step is consider equation of fluid dynamics. So let's make an interval. So interval break till 16:05. So let's relax a little bit. Okay, so let's continue. So now, what's next? So now we have space, which is this lambda, the geometric progression space, and which can be of any dimension, and we have calculus on this space. Calculus in the sense that we can take a sum of the functions, we can take products, and we can take derivatives, and also we have scalar products. So we have all these things. So we can write study equations of motion. So the first example that we consider is Burger's equation. So let's consider inviscid Burgers. So inviscid Burgers equation, recall what it is, du dt plus u multiplied by derivative. So let's write it in a way. So time derivative of u plus u times time derivative of u equals 0. And if we want to work on lattice, we substitute any product by our product. So we have inviscid Burgers equation, and just let's write what it is. So remember that derivative is just ik, and the product is what is here. So let's just write this equation for this product. Okay, so the equation for lambda equal 2. So it becomes du of k dt. And then I will put this term on the right-hand side. It will be minus ik. So what you can write, it's, this can also be written as, remember, this can also be written as 1/2 dx u squared over 2, right? And our product is defined up to a constant, so let's put 2 on the front. No, yeah. 1, 2, 2. No, no 2. It's okay. 1/2. So it will be ux of u. So what it is, it's derivative u multiplied by u over 2. Right? So this will be ik. We take minus because we put into the other side. And then there will be u times u divided by 2. But so these two terms are equal, no? Because it's u and u. And divided by 2, it will give plus. Just 2 will cancel. So it will be u to k by u minus k plus 1/2 of this term, which will be u k over 2 squared. So this is our equation. Okay. The next step is slightly the change of variables. Now, remember that minus k we can remove and put complex conjugation, right? This reality condition. So the next step is you can say that un equal minus I uk, where k is 2 power n. And then this is just to remove this I. So what you get at the end is dun dt will be equal to kn so this term will go first. over 2 to kn minus 1 kn minus 1 square minus kn plus 1 un conjugate. So this is exactly, so this will be the final equation of on our lattice that we constructed for the space, and surprisingly, this is exactly one of the shell models that are very popular. So this is what's called Desnatsky-Novikov or dyadic shell model. So another example that you can try by yourself. So if you consider the same burgers, but with burgers, inviscid burgers, but for golden mean, it gives you Sabra model. Sabra shell model in one of the cases. So somehow, supposing that this strategy of creating space instead of equations also give us the same shell model that we created last time. But what is important is we create Sabra model from Burger's equation, not from 3D Euler. And in principle, this can give us a hint why blow up that we obtained in the Sabra shell model was self-similar. So somehow we can consider it as a analog of the blow up in inviscid Burgers, which is self-similar. So Burger's equation is self-similar, so, and Sabra shell model also gives us some similar blow up. And so this is not surprising. So Sabra shell model from point of view of blow up, it resembles Burgers rather than 3D Euler. So our goal is 3D Euler, and what we do is just consider directly the Euler equations. So incompressible 3D Euler on the lattice, on 3-dimensional lattice. No, actually d-dimensional lattice. Yeah? So it means that we consider U as a function of k and t, where k is a point of the lattice. So we consider a field. So this is our velocity field, but it not lives in any space of physical meaning. It lives in our artificial space. And all we write is exactly the Euler equation. So time derivative of U plus. So U grad U. But remember that we have to put star. It's not normal product. It's our special product in the space. Should be equal minus grad P. And then there will be incompressibility. So just exactly the same equations. But we have different meaning of what means derivative. And we have different meaning of what means product. But operations are the same. So what we can have, okay, so then we can have all the same theorems as we had for Euler. So first of all, let us define Sobolev norm. So analog of Sobolev norm. So HM, so Sobolev norm will be defined as, no, let's define first Lebesgue norm. Lebesgue norm. So Lebesgue norm of L2 will be square root of scalar product, as usual. Then we can also define L infinity norm, which will be just a supremum for all k for absolute values of u of k. U is a vector, so we can just define the usual Lebesgue norm, so L2 and L infinity. And then we can also define the Sobolev norm. So Sobolev norm we will define as L2 norm of the derivative of mth order, and it will be the same as the L2 norm of, so it will be what? It will be, so d with the dm, we just say it's modulus km. So like taking the analog of km's derivative, and so this will be sum k over all points k to m u k squared all 1/2. So in short, you can define Sobolev norm. And it will be Sobolev space, and it's essentially with the same properties. So it will be Hilbert space and so on. So the first theorem that you can prove is about local existence of solution. So this is the first theorem, which resembles the theorem for the 3D Euler equation in original formulation, which tells that you that for any initial condition u0, which is from the Sobolev space with m bigger or equal than 1. So just weaker conditions that we only had 3. So for any initial condition of this kind, and which is incompressible, there exists a unique solution so there exists time t bigger than 0 and unique solution u kt for this interval. So local existence. We can have local existence. Another theorem is about the global existence. So this is exactly Bitcottomide Criterion. So Bitcottomide Criterion tells that either these t's can be taken infinite, or there is maximum time until which you can extend the solution, and that's it. So if this time cannot be extended to infinity, so if there is a blow-up time which is bigger than 0 but smaller than infinity is a blow-up time, then necessarily you have a this Bitcottomide integral, which is exactly the same as in the 3D case. So the integral from 0 to time, the norm of vorticity computed with L infinity norm, so the supremum integrated over time should be infinite, where vorticity is curl of u. This we have, no, we have derivatives. So exactly the same criterion became criterion you have here. Okay, so this is a general structure. Ideas that then we actually have much more. We have all the conservation laws from order equations automatically. So all conservation laws. So we have a conservation of energy, which is defined as a norm, right? So you can define it as scalar product u by 2. It's conserved in Euler. Helicity in the case of 3D. It's defined as scalar product between vorticity and speed, and entropy in the case of 2D. We even have Kelvin theorem. About conservation of circulation. Analog of this Kelvin theorem also can be put here, so just need to formalize it properly. So all the conservation laws are automatically here. Why? Essentially, why is because all the same the operations are all the same. So, for example, let us prove, as an example, let us prove conservation of energy, and let's see how you can prove conservation of energy. So what we need to prove is that derivative of energy in time is 0. Then you just substitute this expression. Then you know how to differentiate the product. So we have this Leibniz rule. And this will become u du dt. And then you substitute all the equations here. So it will be, one term will be u grad pressure, and another term will be u by u grad u. So let's show that these two terms vanish together separately. So what is this? This is, remember, this is scalar product. So this is a sum over all k. No. This is a normal scalar. So it's a sum over all components in d-dimensional space of u, let's put j, uj times derivative of jp. Okay? Now, remember that we have a Leibniz rule, so we can pull this delta to the left-hand side. So this will become dj uj p, but this is incompressibility condition. So 0. So just using the Euler equation, but on lattice, we can find that the first term is 0, and similarly, so take it as an exercise, show that the other term is also 0. It's the same trick, so you write it in components, then put derivatives from one term to the other until you see that all terms cancel because of the incompressibility condition. So essentially, you in one way or the other, you can reproduce all the fluid dynamics, but not all, but big part of the fluid dynamics on a lattice. So we kind of have analog of the fluid dynamics theorem on a lattice, and in particular, we can try to see what happens with a blow-up problem. So we cannot prove the blow-up problem here because it's probably almost as difficult as original, but the advantage is we can make a very clear numerical simulations. So why we can make very clear numerical simulations is because our lattice is very sparse. So we don't need many. We don't really need too many variables in order to simulate a very different what I wanted to also to say. So including that, for example, one of the consequences is that we have entropy conserved, which automatically means that this integral is never infinite. So, for example, you automatically have global regularity for 2 dimensions, but not for 3 dimensions. So what we have on a lattice. So remember, the lattice starts with 1 lambda, with 1, then with lambda, then lambda squared, and so on, and like this in all directions. So you see, if you want to span a huge amount of scales, you still don't need many variables. Just because they go with bigger distance, which means that you, in principle, can make a very safe numerical simulation with high accuracy, with in a very big domain, and see whether you do have blow up or not, and then we can see what kind of blow up it is. So I think that I will show the results of simulations, and then we discuss what this means for. I forgot the connector. Wait for 2 minutes. I bring the connector and we'll be back. of this blow up. So what you can see, it goes to 0 like linearly, but with all these different fluctuations. So the next picture that we can look is we can look how we approach the blow up time. So this is different to blow up time and maximum vorticity and maximum vorticity, how it changes. So this log scale. So we can clearly see that vorticity goes to 0 as inverse time. So this is a law. Power vorticity goes to infinity as a power law. But again, with all these different oscillations. Okay, this is the energy spectrum evolution, but we will not discuss it here. So what is we can see? What will be more interesting is to see really evolution. So the evolution of the system and evolution of the system. So in order to see evolution of the system, can we switch to the blackboard? No? So in order to see evolution of the system, we need to write it in proper coordinates. So we have, certainly I will not draw up my solution on lattice as it is, right? Because it's huge. So what I will do is I will collapse this lattice to the normal situation. So I will write logs, log k1, log lambda k2, and so on. So then it becomes a normal regular lattice. So I will write it. This is just a good way in order to represent a lattice which is has a form of geometric progression. Is take a logarithm of each coordinate, so it becomes a normal lattice with plus and minus. And then I will also, since I took logs of coordinates, then I also want to define a new variable which will be minus log of blow-up time minus normal time. So you see what it is. So when time approaches to blow-up time, logarithm goes to minus infinity. This minus cancels minus. So when as time comes to the blow-up time, the tau goes to infinity. So we have a new time variable and slightly different representation of the logarithmic lattice. So now we will see how the simulation look like. Then we have video. So what it is, it's this three-dimensional space. So you see it's K1, K2, K3. So they're just written in a logarithmic way. You see, so it's 1, 10,000, 10 millions, and so on. No? So 10 power 8, 10 power 12, 10 power 16. So we have a logarithmic space for each coordinate. So if you have logarithmic axis, your lattice look uniform, right? So you can see this. I cannot expand it. So you can see this. So each point is a point of the lattice. And then in order to represent a three-dimensional picture, we just make two cuts. We make two planes, and we will plot our function by color on these two cuts. What is plotted is vorticity, and vorticity is plotted at the point where it's bigger than certain threshold. So when it's too small, we just leave it blank. The time will be written here above. So as tau goes to plus infinity, we approach the blow up, and we will just see what happens. So you see how the solution evolves, and it goes to smaller and smaller scales. Smaller scales means bigger and bigger k. So what you see is, again, it's a wave, but it's quite a different wave. So it's different in two aspects. First of all, it doesn't have exactly the same form all the time. So it's a wave which always changes. It has overall shape is the same, but details are always different. So if we just see it again, so you see that the details are always change. So this leads us to the conjecture that we can actually verify also numerically. Conjecture. That you can formulate that that the blow up in 3D incompressible Euler equations on the lattice develops as a chaotic wave in these log ki tau variables. There are a bit more than this in this conjecture, but just let's stop on the most important part. So we conjecture that the blow-up exists, but it develops a chaotic wave. We can check that it's chaotic wave because you can compute very clearly how the two nearby solutions separate in time. So you start with the solutions which are very, very close to each other and start to see how the separation goes in time. And you see clearly the exponential separation, which is a direct property of any chaotic behavior, because it means that there is a positive Lyapunov exponent. So this can be checked. And essentially, this is about form of the development. So it's not exactly self-similar. It's chaotic. So every time, you have limiting behavior, but it's chaotic limiting behavior. So you never see exactly the same property. So this somehow resembles what we see in direct simulations of the 3D Euler equations in a normal physical space. But there is a much more important issue. And much more important issue is shown in this picture. So this is the snapshots of these waves at different times. And and the main part that you have to notice is that the form of this attractor, of this wave, has this kind of butterfly form, but what's important is the size. So you see the size, here it's 10 power 4, here's 10 power 12. So the core of the size is at least 6 orders of magnitude in difference of scale. So the size of this wave, which will be very, very huge here. So the size of this wave in the dimensions is something like 10 power 6. So the size of the wave is about 10 power 6 in a difference of scales. And this is a lot. This is a lot because if you think about this structure in the only reason why we can capture such structure with logarithmic lattice is because our spacing becoming bigger and bigger. So it's actually not a big problem to capture this range of scales. But in a normal, in a real space, in a real physical space, which will be T3 or R3, so what you need numerically in order to capture this kind of resolution, we would need a resolution. So in each direction, it's 10 power 6. So it's in space. And also at least the same in time. So this gives you 10 power 24 points in order to compute your solution. And the resources that you will need to in order to make this simulation just in a memory, it means that you have to keep 10 power 24 points in a memory. And when I just recalled you that 1 terabyte is 10 power 12. So this is 12 orders of magnitude less than we would need in order to capture this kind of structure. So, so this shell model, this toy model showed that we do have blow up. It does have a structure which can be in principle verified numerically. But if the same structure will appear in a real space, you are still 10,000 billions times less resources you have than this. And I think this should be around coming close to the whole memory that we have available nowadays. No? Huh? It's Avogadro number, yeah. Okay. So we are very, very far away from this. So it's in principle, but very, very far away. So now, we can play around. So for example, what was quite surprising for us, where it is? Is, let me see, here. So what was very surprising for us is that we have several models. We have a model with a golden mean, and we also have a model with a plastic number. And these are two different models, and we can check blow up in two different models, and you can see that they're quite very, very similar. So with a golden mean shown here above and a plastic number below, so you see it's much better resolved. So plastic number lambda is smaller, and you see that essentially it's the same structure. So the structure changes, but it's essentially the same structure shown in very different models. So and both models, the space is different, but the equations are exactly three-dimensional Euler equations. So we have a certain rigidity that we see numerically. And another aspect that you can see numerically is how the maximum vorticity is growing in time. So this is a log of entropy, for example. So log of entropy, and log was used in some works of numerical simulations in order to show that the tendency to blow up, it's kind of degrading. So if you plot log in time, so this is log of our simulation. So it first looks like it's going down, but then it turns and goes up and blows up. So this is a blow up time, and this is a resolution where we would have to stop if we make direct numerical simulations with the best resolution which is accessible right now. So you see that if you do the direct numerical simulation with this model and stop where we would stop today with the best computers, you will stop here, and you would mostly say that there is no blow up, because this curve kind of shows that it will not turn up to infinity in finite time, no? Because it has kind of negative second derivative. So the conclusion is that the model that we present looks to be rather in agreement with all numerical simulation we have, and the conclusions are somewhat pessimistic that the blow-up can be, but numerically it's hardly accessible. So you need to find either other ways to see it, or numerical, or analytical, and so on. So they're just pushing straight the usual direct numerical simulation doesn't give you much hope to resolve it if the situation is like what our toy model shows. So I think that's good for today. So now, yes.
Following a chaotic wave is something of a measure.
Yes.
It's a measure which is propagating.
Yeah.
It's a measure which is propagating with the chaotic property.
Well, it's a measure which is in a limit. It's a measure in a limit with a chaotic property. We could measure what we could verify that it has positive Lyapunov exponent. So this kind of guarantee that it's chaotic. More than that, it's difficult to say, but in a limit it becomes a measure. Yes, in a limit it becomes a measure. So essentially, what it means that if you want to see blow up, a very small error will close to blow up already gives you different results. And there were very recent results. I forgot who did it. So who even proved something like this? So there was 2 years ago, I think it was a result of proving that if blow up in Euler, 3D Euler exists, it should be sensitive to the perturbation. Yeah, exactly.
Wouldn't they have to, I might be taking this wrong, wouldn't they have to reach some infinite velocity in order to reach infinite resolution for the blow-up to happen? Or can blow-up happen still at finite resolution?
No, it goes to infinity. So it means that it goes to infinity in K-space, which is exactly what it goes to infinity, and at the same time as a structure goes to infinity, the amplitude of the vorticity goes to infinity as well. So it goes to infinity, and also it increases in amplitude.
But then wouldn't that be like for t going to infinity?
For tau going to infinity.
Sure. Yeah. So in principle, there is not finite time.
No, this is finite. This is infinite tau. But tau goes to infinity with time goes to finite TB. Yeah, so that's exactly this variable in order to stretch this final behavior close to the blow-up time. So we come to blow-up time, but in order to see how it goes, we stretch it with a logarithm. And then you see the wave. So this is kind of opening stretching the last stage of what happens near blow up in order to see the dynamics.
Yeah. Time scale that the way. But okay, and also, is there a chance? I mean, of course, there's that all of this phenomenon is in fact due to the somewhat arbitrary choice of that product that you made, right at the beginning. Because it's an unusual format for a product, right? And why should we expect that just because it follows all those conditions that it would generate a model that is comparable in some sense to reality?
Yeah, that's very, very correct. So we don't have. So the philosophy is like this. So we try to create simpler models. So whenever you create simpler model, you lose some properties. You never know that if this property is really important or not. So you have different system, and you study the system, has some conclusions. So certainly you don't have a guarantee that the same conclusion is valid for the original system. So what we see here is that at least for two different products that we have, which are by themselves disappeared. Here. So the two different products, one for gold and mean and another for plastic, which by themselves are two very different products, we have very similar picture. So this gives us hope that this may be correct. But certainly, we have no guarantee that this is what happens with all. Just this gives you another scenario that can happen. And this scenario, unlike the previous one, is not in contradictions with direct simulation, with direct observation. So it's not. You cannot say that it's in agreement with direct simulations, numerical simulations, because direct numerical simulations are not really conclusive. But at least it does not contradict them.
I guess my question was more in the line of, is there any kind of perhaps physical intuition for why the product should be defined like that? Or was it just like purely mathematical?
No, it's purely mathematical. No, it's purely mathematical. Essentially, it's not even purely mathematical. It's even more rigid, because whenever you take this space, you just have two products, actually three, but with lambda equal 2 doesn't work. So just two products that you can test. That's it. So any space of this kind just give you two types of product that you can test, and we tested them. And that's it. So and it gave some very different scenario from what we had with other toy models. So that's possible suggestion, which you can try in real 3D Euler if you can reach it, if you can reach this resolution, maybe. Or you just give up to do numerical simulation and start proving it. No, lambda equal 2, it actually gives a trivial model, because when lambda equal 2, because of incompressibility, it gives a model which just does not evolve. Whatever dimension is, yeah. It just does not have a coupling to smaller scales. Yeah, so it's just not enough couplings in order to make any real evolutionary model. So for this reason, there are only two models with golden mean and plastic number which can work. And surprisingly, they work. So it's a thing that already.
Sorry, does the model for lambda equals 2 not work?
Lambda 2 equal doesn't work. Yeah, lambda just because this model becomes somewhat trivial. Remember that lambda equal 2, it had just three terms in the product, and when you put extra condition, some of them cancel, and you just have insufficient terms on the right-hand side in order to have evolution. Okay, so we're good, and so our next step will be that we finish with the blow-up topic. There will be still one short half a lecture, but maybe in 1-2 weeks, because Andre said he want to study these L-Gindi proofs and give us a short summary of what is done there. So for 1 hour, so there is a volunteer. But this will not be very soon. So from tomorrow we move to a different topic, which is spontaneous stochasticity. And in principle, the topic is about what is after blow up. Okay, so so we have all equations. It may blow up in finite time. We don't know if it blows up in finite time or not, but it in principle does not. In principle, we can ask the question, okay, it blows up, so what is next? So how we can understand the solution after the blow up? And we have the solution because, remember, it's not Euler that interests us, but Navier-Stokes. And Navier-Stokes has solution for all the times. And now Navier-Stokes we have interest in the Navier-Stokes in a turbulent regime, which means that when viscosity goes to 0. When viscosity goes to 0, when you put it to 0, it's Euler. Euler behaves well until finite time, but not after. So what is there? So what is after? I probably give you. So we have time axis. And we have a Navier-Stokes equation, which is everywhere is all right, from initial moment to the infinite. So now we want to take viscosity going to 0. So this is turbulence. If you just put viscosity to 0, you take Euler. You have Euler. So viscosity equals 0 is Euler. As long as Euler is all right, so until they blow up, we can expect that there is a convergence. So this is exactly what you get from Navier-Stokes. But when Euler blows up, we cannot extend it. So what is here? So in which sense you can understand the solution, which is a limit of the Navier-Stokes, to Euler, when Euler already does not, solution of Euler already exploded. And this is where the new topic starts. It's about spontaneous stochasticity. And we mainly will discuss also simplified model, because only there something can be set. And actually, this will be even more simplified model than this. So we started tomorrow. And the next 3 lectures will be given by Simon Talabar. So he is a professor from University in Nice. And then I'll be back giving lectures. So see you tomorrow. Thank you.